Good morning. Today we are going to discuss about thermodynamics. Thermodynamics means we get Joule's law, zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics, different thermodynamic process, isothermal, adiabatic, isobaric, isochoric, and heat engine, refrigerator also come here, and the Carnot cycle, and specific heats of gases CP CV. About CP CV, the relation between them, etc. we can get. So thermodynamics we can get two videos. So first part we can see laws of thermodynamics and heat engine, refrigerator, and different thermodynamic process. Okay. Actually, thermodynamics is the branch of physics. Thermodynamics is the branch of physics which you can deal the relation between mechanical work and heat produced. Whenever work is done, there will be heat generated. The work done is equal to some constant into Q. Whenever work is done, heat generates. That is what we observed. Then the relation between mechanical work and heat observed we can obtain in thermodynamics. So in the thermodynamics, four laws: Joule's law, zeroth law of thermodynamics, first law, second law of thermodynamics, heat engine, refrigerator. So we can see in this video. Okay. So first one, Joule's law. Whenever work is done, heat is generated. What is the relation between them? The work done is directly proportional to heat generated. W proportional to Q. W is equal to JQ. J is called Joule's constant or mechanical equivalent of heat. J is called mechanical equivalent of heat. And in SI system, J is equal to 1. SI system, J is equal to 1. Practical system means heat energy measured in calorie, work done measured in joule. Then J value in practical system, J is equal to 4.186, approximately 4.2 joule per calorie. 4.2, J is equal to 4.2 joule per calorie. And 1 calorie definition, calorie definition: amount of heat energy required to rise the temperature of water of mass 1 gram from 14.5 degrees centigrade to 15.5 degrees centigrade. That means by 1 degree centigrade. That is calorie. Amount of heat required to rise the temperature of water of mass 1 gram by 1 degree centigrade. Therefore, 1 calorie is equal to 4.186 joules, or approximately 4.2 joules. 1 calorie, 4.2 joules. And Joule's law, W is equal to JQ. W is equal to JQ. Better take, while we are doing the problem in SI system, not a problem. J is equal to 1. Then all values are in SI system. But in a practical system, we know some values. Specific heat of water 1, specific heat of ice 0.5, L of ice 80 calorie per gram, L of water, L of steam 540 calorie per gram. These values calorie per gram. These values they will not give an exam, but even though we remember that and we can do the problems. Even though not given, also not a problem. But SI system remember, they have to give also. So that's why if we apply this side SI system and this side CGS system better. So W is equal to JQ. This part we apply SI system and this part apply practical system or CGS system. Then take J value as 4.2. Then problems easily can solve. For example, from a height of 100 meter, water is falling. Waterfall height 100 meter. Calculate rising temperature of water on reaching to the ground. Water is falling from 100 meter. W is equal to JQ. So W means mgh because water having potential energy. J into rising temperature is required. Q is equal to ms d theta. Then apply this side SI system, this side is practical system or CGS system. CGS system apply. So mass M, G 10, height 100 they given, 100 meters height of the waterfall is equal to J 4.2. Mass here M kg, mass is in kilogram. In CGS system mass is in grams. M into 1000 grams into specific heat of water is 1 because already we know specific heat of water, specific heat of ice, etc. into d theta. Now we cancel M both sides. So 1000 cancelled, this side also 1000. Therefore d theta is equal to 1 by 4.2. 1 by 4.2 means approximately 0.25 degrees centigrade. Rising temperature of water 0.25. And one more problem. Ice cube at 0 degrees centigrade is dropped from a large height, but on reaching to the ground, just it is melted. On reaching to the ground, it is melted. Calculate the height from which the height ice cube is dropped. Ice cube is at 0 degrees centigrade. Then mgh is equal to J into ml. Ice is melting. Okay, mm cancel. H is equal to JL by G. SI system use this one. J value also 1. J value also 1. But in practical system, how to do this problem is mgh is equal to J into ml. M G height we have to calculate. Height J value 4.2. Mass M is 1000 grams. 1000 M. Into L value 80. L value 80. 80 calorie per gram. Latent heat of ice 80. Therefore, M cancel. 0 cancel. And H is equal to 4.42 into 800. 8 2s are 16, 1, 8 4s 32 plus 1, 33, 2 zeros, 33,600 meter or 33.6 kilometer. So this is the ice cube height from which the ice cube is dropped such that it just melted completely on reaching to the ground. Ice cube just melts on reaching to the ground. If you drop it from a height of 33.6 kilometer, and this height is independent of mass. The height is independent of mass. Even though 1 gram or 1 kilogram, if it dropped from this height, it just melts on reaching to the ground. Next, one more important problem. Bullet fired with speed v hits the target and 50% of energy transferred to the target, remaining 50% of energy absorbed by the bullet. Calculate the rising temperature of the bullet. So W is equal to JQ. W, kinetic energy of the bullet, half mv square is equal to J into only 50% of kinetic energy absorbed by the bullet. So in this 50% means half. half of m square is equal to j into ms d theta. From this we calculate the rising temperature of the bullet. The rising temperature. Or one problem, bullet fired, temperature rising. Bullet velocity doubled. What happened to the rising temperature? So velocity square directly proportional to d theta. V square proportional to d theta. Next case, velocity of the bullet doubled means the temperature rises by 4 times because d theta proportional to v square. Velocity doubled means it is increased by 4 times. That is one problem. And from this one we can do one problem. This one you have to calculate d theta. They can give mass of the bullet and the specific of the bullet is required. Lead bullet means 0.03. Let specific it 0.03. And mass cancel j value we know, we can do the problem. SI system means they can give the S value and the j value is 1. That is also not a problem. But practical systems, the data sufficient to not given means you have to use S is equal to 0.03. That means mercury 0.033, lead is 0.03, specific heat of lead, least for lead. Okay, so this is about the Jones law. And the thermodynamics laws, there are 3 laws of thermodynamics. One is zeroth law. Zeroth law of thermodynamics. There are 2 bodies A and B. Another body C also there. Here A and B are in thermal equilibrium. Thermal equilibrium means both are at the same temperature. And B and C are also in thermal equilibrium. B and C are also at the same temperature. Same temperature means thermal equilibrium. Heat will not transfer. Then the both A and B are also in thermal equilibrium. These two are also in thermal equilibrium. That is zeroth law. If 2 bodies A and B are in thermal equilibrium with the third body C, then the 2 bodies are also in thermal equilibrium with each other. That is zeroth law of thermodynamics. What is importance of this means temperature of the body defined by zeroth law. Temperature of the body defined by zeroth law of thermodynamics. Next about first law of thermodynamics. First law of thermodynamics. First law states that for a system, suppose heat is supplied, heat energy is supplied, and then that heat energy is utilized to increase its internal energy, some part utilized to increase its internal energy, and some part utilized for work done. Some part utilized for work done. This is first law of thermodynamics. It is based on the conservation of energy. Heat supplied to a system is equal to sum of increase in its internal energy and work done by the system. This is first law of thermodynamics. Okay, and you can write this one as dq is equal to du plus pdv also, referring to change in volume. Here sign conventions important. Sign conventions. Heat energy supplied to a system. Heat supplied. Then dq positive. Heat supplied means dq positive. Heat released from the system. Heat released. dq negative. Heat released means dq negative. And work done on the gas. Work done on the gas. That means gas is compressing. So work done on the gas negative. So dW negative. Work done on the gas means gas compressing. dV negative. So that's why dW also negative. Work done by the gas. Work done by the gas. Then dW positive. Here dW negative, here dW positive. So these are the sign conventions. We have to calculate du. change in internal energy. You have to calculate the change in internal energy. If you calculate the change in internal energy and that is positive, then you say internal energy increased. If it is negative, then you have to say internal energy decreases. Internal energy decreases. Okay? Now we can do one problem based on first law of thermodynamics. For a system, 300 joules of heat energy supplied. dQ heat supplied. So plus 300. And 100 joules of work is done on it. So work done on it is 100 joules. But work done on the system negative. Initial internal energy is 20 joule. Find the final internal energy. Question. So we know first law of thermodynamics, dQ is equal to du plus dW. du is not internal energy. It is the change in internal energy. Therefore, heat supplied. So plus 300 is equal to du minus 100 because work done on the system negative. Therefore, du is equal to 400 joules. du means the U final internal energy minus initial internal energy 400. Therefore, U final is equal to du value 20 they given. So the ui value 20 they given. So bring this side 420 joules. The final internal energy, because this is 20 joules, the final internal energy is 420 joules. So this is first law of thermodynamics. Okay? And what about the second law of thermodynamics? Second law of thermodynamics gives the direction of flow of heat energy. And the first law gives the conservation of energy. Direction of the heat flow given by second law. Second law of thermodynamics. Second law of thermodynamics states that generally heat flows from high temperature to low temperature. But low temperature to high temperature heat will not flow. That is explained by second law of thermodynamics. So it is impossible for the transfer of heat from low temperature to high temperature without help of any external agency. That means with the help of external agency possible. In the refrigerator, from high temperature to the low temperature, we are transferring. From low temperature to high temperature, we are transferring the heat. Actually, we kept water inside. That temperature is 20, and outside temperature also 25. Now, from 20 to 25, we are sending heat. But practically not possible without the help of external agency according to second law. We are using refrigerator mission. That's why we are sending heat from 20 degree centigrade water bottle to outside temperature 25 or 30. So heat is transferring from low temperature to high temperature. That is the second law of thermodynamics. With the help of external agency, it is possible. Without the help of external agency, it is not possible. Okay. Next, second model, Kelvin statement. The class is statement. Kelvin statement of second law of thermodynamics is you are doing work heat generating, but it is impossible to convert total work done into heat energy. Total work done into heat energy. Not possible to convert total work into heat energy. And from heat energy, we can't extract total work. From heat energy, we cannot get total work done. Work done, we cannot extract work from the heat energy. 100% work heat energy we are unable to convert into work done. That is the second law of thermodynamics. Actually, whenever work is done, heat is generated. Suppose heat energy is there, can we get the work done from it? Yes, we are getting, but few percent only we are getting, not 100%. That is second law of thermodynamics. It is impossible to convert total heat energy into mechanical work. That means some percentage, 60%, 70% we can do. But total heat cannot be converted. Heat engine. Earlier days, train also moving with the heat engine only. So there we convert the heat energy either 60 or 70% into work done. We can't convert the total heat into mechanical work. If it is possible, in the nature we have lot of heat energy. Because of sunlight, we have lot of heat energy. Sea water, because daytime the water become hot and the entire water is hot. Then from that heat energy, hot water, can we get work done means not possible, totally not possible, only few part only possible. So that is the second law of thermodynamics. It states that it is impossible to convert total heat into mechanical work. So that is second law. Okay. Kelvin statement and Clausius statements. Two statements are there. Next, about heat engine and the refrigerator. This is the source at a temperature of T1. This one is the low temperature sink, temperature of T2, and some working substance is taken here. And we are transferring the heat from source to the sink through the working substance. Then the working substance, this is a working substance. Substance can produce the work done. It can generate some work. When heat energy transferring from high temperature to low temperature through the working substance can do some work. This is the principle of heat engine. Then how much work it is producing? That is called efficiency. Efficiency of heat engine. It is represented by eta is equal to work done by the working substance by heat transferred, Q1 heat transferred from source, and finally sink got the heat energy Q2. So by heat transferred, W by Q. What is work done by the working substance? The difference of heat energy is work done. Therefore, eta is equal to Q1 minus Q2 by Q1. This is the efficiency of the heat engine. Therefore, eta is equal to 1 minus Q2 by Q1. In percentage, if you want, into 100. And heat energy proportional to temperature. So you can write this one as eta is equal to 1 minus T2 by T1 into 100. This is the efficiency of the heat engine. Efficiency of the heat engine. You get a high efficiency if temperature of the sink is 0 Kelvin. If it is 0 Kelvin, so this is 0. So eta is equal to 100%. Eta is equal to 100%. So this is about the heat engine. Next about the refrigerator. In the refrigerator, from sink temperature T2, we are sending the heat to the source, high temperature source, and some external work is done on the working substance. We are doing the work. Then we are transferring the heat low temperature to high temperature. We are transferring the heat from low temperature to high temperature with the help of external agency. This is the principle of refrigerator and the coefficient of performance of refrigerator. We call it as beta. Coefficient or performance of refrigerator. It is represented by beta. Coefficient of performance of refrigerator is equal to Q2 by Q1 minus Q2. This is the coefficient of performance of refrigerator. That means Q2, heat extracted from the sink by work done by the external agency, Q1 minus Q2. So this is called coefficient of performance of refrigerator. Efficiency and coefficient of performance having no units. And you can write this one as PU by P1 minus P2 also. This is beta. Now we can apply the relation between eta and beta. Already we know eta is equal to 1 minus T2 by T1. 1 minus T2 by T1. Or we can write it as T1 minus T2 by T1. This is eta. This is eta. Now multiply eta and beta. If we multiply eta and beta, we are getting T2 by T1. T2 by T1. Because this part cancel. T2 by T1. But T2 by T1 is T2 by T1. And we know eta is equal to 1 minus T2 by T1. Therefore, T2 by T1 is equal to 1 minus eta. So that is 1 minus eta. Therefore, beta is equal to 1 minus eta by eta. Some relation between eta and beta. Or eta is equal to, if you want the eta, bring this one this side and take common. Eta is equal to 1 by 1 plus beta. 1 by 1 plus beta. So these are the relation between eta and beta. Eta and beta. 1 by 1 plus beta. Okay. So this is about the thermodynamics first part. So thermodynamics contains Joule's law, zeroth law, first law, second law, refrigerator and heat engine. Heat engine, Carnot engine or heat engine same. And the refrigerator, which instrument convert heat energy into mechanical work. And Carnot engine or heat engine. Which instrument transfers the heat from low temperature to high temperature? The refrigerator. Refrigerator transfers the heat from low temperature to high temperature. First of thermodynamics based on the conservation of energy. According to first law, energy is conserved. Which law of thermodynamics define the temperature? Zeroth law define temperature of the body. Zeroth law define the temperature of the body. Which law of thermodynamics gives the direction of the flow of heat? Direction of the flow of heat is given by second law of thermodynamics. Second law of thermodynamics gives the direction of the flow of heat energy. Okay? And these are the different topics of thermodynamics. Main formulas first of thermodynamics. dU is equal to dU plus dW. Eta is equal to 1 minus T2 by T1. Beta is equal to T2 by T1 minus T2. And W is equal to JQ. W is equal to JQ. Conversion of joules into calories, calories into joules. 1 calorie is equal to 4.2 joules. Or 1 joule is 1 by 4.2 calories. 1 joule is equal to 1 by 4.2 calories. Okay. right?